Assalamualaikum and a very good day to everyone. Now, today we are from Group A. We're going to present hydrocarbon potential delineation using Poisson ratio reflectivity. Now, before I go any further, I would like to introduce our team members, which is the first, my name is Muhammad Isyraf, and the second is Muhammad Zaki Naufal, the third is Muhammad Haziq, and lastly is Amir Ariff. Now, let us go to the first outline for our presentation for today. Now, the first part, which is the introduction, where I will explain to you briefly about the project itself and also the objective as to why we conduct this project. Next, we have the methodology, such as what methods did we use to conduct for this project. And the third outline for our presentation is the results and discussion. Okay, so we'll show to you our results based on the methodology that we have used. And last but not least is the conclusion itself. Now let us go to the first outline, the introduction. Okay, now when it comes to hydrocarbon delineation, most of the researchers frequently prefer acoustic impedance and also shear impedance. In this project, we will prove that Poisson ratio is useful in hydrocarbon delineation. To identify the bright spot is typically determined by the product of intercept and also gradient, and in this paper, we will detect the hydrocarbon presence using Poisson ratio AVO attribute. Okay, now to prove this statement, where we use hydrocarbon to detect we use the Poisson ratio to detect the hydrocarbon presence. There are two objectives that we need to achieve. Okay, now let us proceed with the objectives for our project. Now, the first objective, which is to delineate hydrocarbon cluster based on cross-plotting of selected logs data, and the second is to analyze characteristic of hydrocarbon indicator using scale Poisson ratio change. Now, without further ado, I will pass to the next presenter to discuss further about our methodology that we use for this project. Thank you.
Okay, next is the methodology used for this simulation. So the methodology consists of 4 main steps, and all of these methodology are done using the Hampton-Russell software. So the first methodology is the FRM, which is known as the fluid replacing model. The objective for this step is to manipulate the well log and to perform gas matte fluid substitution. And the parameters used for these steps is reservoir interval, the velocity, density, and in situ fluid. The second step is elastic properties. The objective of this step is to calculate the elastic properties for each fluid type and display the cross plot. The parameter used for this step is density, P impedance, S impedance, VPVS ratio, Poisson ratio, and lambda mu rho. Moving on to the third step, which is the AVO modeling. So the purpose of this step is to create synthetic gather, and the parameter used are seismic wavelet, seismic geometry, and depth to time conversion. And the last step is AVO analysis on 2D data, which is mainly to perform AVO analysis on the real CDP gatherers. Okay, next I'm going to discuss on the result and discussion on the simulation. So the result and discussion, which are mainly the crossplot that have been generated during the second step, which is the elastic properties step. Moving on to the first crossplot, which is the gamma ray versus Poisson ratio. The red polygon is representing the gas sand, the green polygon is representing the oil sand, and the blue polygon is representing the brine sand. So the Poisson ratio for the brine Poisson ratio ranges from 0.32 to 0.4. The Poisson ratio for oil ranges from 0.24 to 0.31, and the Poisson ratio for gas ranges from 0.07 to 0.19. From the figure, we can observe that for all fluid type, the gamma ray ranges from 60 to 80 API, and there is a strong shell line formed particularly at 95 API. So for this gamma ray versus Poisson ratio crossplot, it is quite difficult to delineating the polygon. Firstly, because the brine saturated from the brine saturated polygon, we can observe that the points are mixed with the lithology traces, which is the shell. And for oil saturated polygon, it is in indeterministic area boundary. Moving on to the second crossplot, which is the P wave impedance versus the Poisson ratio. From this figure here, we can observe that the P impedance for brine ranges from 6,000 to 7,500. The P impedance for oil ranges from 5,300 to 7,000, and the gas P impedance ranges from 4,500 to 6,400. Whereas the Poisson ratio for brine ranges from 0.3 to 0.35. The Poisson ratio for oil ranges from 0.24 to 0.3, and gas ranges from 0.15 to 0.22. From the figure here, we can observe that the points align, mostly all of the points are aligned parallel to the shear line, and the polygons are evenly spaced and shift in stacking towards right. So for the PVF impedance versus the Poisson ratio crossplot, it is more easier to delineating the hydrocarbon compared to the previous crossplot.
Everyone, my name is Zaki Naufal. I would like to continue our presentation on the result of our crossplot. So in this slide, we can see the crossplot of S-wave impedance versus Poisson ratio. And as you can see, the delineation of fluid type, which are gas in the red polygons, oil in the green polygons, and the blue ones shows the brine. So it can be shown that points the line parallel to the shell line on top, and the polygons are evenly spaced and stacked horizontally. And so this crossplot can be a significant hydrocarbon delineation indicator. Now we move on to the VPVS versus Poisson ratio crossplot. So as you can see here, the points aligned along the inclining curve line, as you can see in the picture here, with the top one is the brine, and then going down will be oil, and the bottom one will be the gas zone. These polygons are closely formed along the curve and terminated, then it will continue to produce the other fluid type. So also this crossplot can be used as a sequential hydrocarbon delineation. And this is the next will be the lambda rho versus Poisson ratio. And as you can see here, the gas zone is completely far from the oil and brine, so it will be a good indicator for the gas zone. As you can see also, the lambda rho increases from gas to oil and then brine, and the shell line forms in the gentle sloping here at the right side, and the polygons are widely spaced in various orientation, and this also can be a good indicator of hydrocarbon, especially the gas. Now we move on to the mu rho versus Poisson ratio. Same with the previous crossplot, this mu rho also shows the gas zone. It's very clearly identified in the left side here. So the mu rho shows the decreasing from gas to oil to brine, and the shell line forms in the concave curve at the right side, and the points align distinctively, forming coherent lines. as you can see here in the determination of the oil and the brine. So we could say that this Muro and Poisson ratio cross plot is a good indicator of hydrocarbon delineation, especially for gas. Alright, so move on to the density and Poisson ratio cross plot. As you can see here, the shell line at the right side, it's formed vertically at 2.28 gram per cc, and also the things that we can identify is the behaviors of the points with the increasing of Poisson ratio. For brine itself, the points are look tied to sparse, and then for oil zone, the points tend to be sparse to linear, and for gas zone, the points behavior tends to be linear to sparse. So from this crossplot also shows the good indicator of hydrocarbon delineation, because as we can see here, the gas zone and the oil zone can be identified uh, in a good way. So next, move on to the resistivity versus Poisson ratio. In this crossplot, uh, is a bit different because the resistivity ranges from the 6 to 12 ohm meter for all fluid types, and the shell lines is vertically formed with poor delineation. So the shell lines, as we can see here, it's located somewhere around 2 to 6 ohm meter, and also the points are sparsely distributed. This can be distinguished based on approximately formed points. However, in the as you can see in the oil zone here in the middle, there are some outliers points from the bottom to the top. Same goes with the brine. The points itself mixed with the shell, so it's hard to identify. So from this cross plot, we can say that it's not really a good indicator for the hydrocarbon delineation.
Thank you, Mr. Naufal, for the cross-plot analysis. My name is Amir, and now I would like to present on cross-plot reference. Here in the screen, there is four types of cross-plot that is typically used in many papers. First, P impedance versus S impedance. As you can see, the reference line are all parallel to the shale line, being the gas sand further from the shale line, whereas brine sand located near to the shale line. The second cross plot line are VPVS versus Poisson ratio. In this cross plot, the hydrocarbon sand is delineated based on uh, VPVS value and also Poisson ratio value. With that being said, gas sand has the low VPVS and also Poisson ratio value, whereas shale has the high VPVS and also Poisson ratio value. The third crossplot is the lambda mu rho crossplot. In this crossplot, as you can see, the gas sand located in the left, whereas the brine sand is located towards the right. And lastly, in the final crossplot, which is density versus Poisson ratio, you can see that the shale lithology is located on the top right, whereas for the gas sand is located on the bottom left. Based on cross-plot relationship between various parameters with Poisson ratio, the typical pattern developed throughout all crossplot is that gas sand appears furthest from shale line, followed by oil sand in the middle, and then brine sand form closest to shale line. The general Poisson ratio reading obtained throughout the cross plot as follows: brine sand from 0.31 until 0.40, oil sand from 0.22 until 0.31, and lastly gas sand from 0.07 until 0.22. The cross plot with good hydrocarbon delineation are acoustic impedance versus Poisson ratio, shear impedance versus Poisson ratio, VP-Vs ratio versus Poisson ratio, lambda rho versus Poisson ratio, mu rho versus Poisson ratio, and lastly density versus Poisson ratio. But in the downside, the cross plot with poor hydrocarbon delineation are gamma ray versus Poisson ratio and also resistivity versus Poisson ratio. The next analysis is on amplitude variation with offset. The graph shown is the product of gradient with intercept. As you can see, the gas sand layer shown at the depth of 600 meter show highly positive product value indicated by red color for both top and base sand. And this effect decreases with offset. Therefore, the effect produced by gas sand layer is delineated as dim out effect. Therefore, the AVO class for dim out is classified as class 1 AVO for this particular gas sand. As for the conclusion for this paper, we will touch a little bit on seismic trace evaluation. Using a tight seismic data, the hydrocarbon bearing sand layer can be delineated as the following. For top sand, the seismic wavelet shows trough of negative amplitude, thus giving the impression of dim out in seismic section, resulting from the decreasing reflection coefficient of seismic wave travels from shale to gas sand. And also for the base sand, the seismic wavelet shows crest of positive amplitude, thus giving the impression of bright spot in the seismic section, resulting from the increasing reflection coefficient of seismic wave travels from gas sand to shale. And to continue for the next evaluation, I shall now pass to Mr. Isyraf.
Hi, hello again. So this part is the continuation for the seismic trace evaluation. Okay, now before I go any further, just a quick recap for what these colors mean. Okay, so for this red dot here is indicating gas presence. The green dot in the middle section is oil. The blue dot here is indicating brine or water, and last but not least, the green dot here is indicating shale lithology. Now, if you look at the cross plot, the gas sand has low Poisson ratio. It is between 0.15 to 0.2. Okay, and also and its trace points are established further from the massive cluster of lithology. Next, the oil sand trace points are within the Poisson ratio range of 0.25 to 0.3. So this is how we use the cross plot to interpret the seismic trace versus the Poisson ratio. Okay, now for the last slide, okay, we have the AVO analysis based on the scale Poisson ratio change. Okay, we can see here the gas sand layer shows negative value for Poisson ratio scale. Here, the rectangular box here, where it shows from blue to orange, and by using the scale here, we can see it's showing a negative value. So for both upper and lower shale show positive value for Poisson ratio scale, and the transition zone from shale to sand layer show decrease in Poisson ratio reading. Now this is because the gas sand has low Poisson ratio. So we hope that from our presentation today, we have managed to prove that we can use Poisson ratio to delineate hydrocarbon. So that's all from our presentation for today. I hope you enjoyed the presentation. With that, thank you and Assalamualaikum and have a nice day.